Welcome to our video on learning from end-user data with Shuffled Differential Privacy over Kernel Densities. The problem we are going to solve here is private distributed topical decoding. So we have a network of users, each one of them has a private text. They communicate with a central untrusted server whose goal is to detect the topical themes of the texts or what the user texts are about without actually reading any of the texts in order to preserve user privacy. For example, today, many people use healthcare apps on their smartphones to communicate with their doctors and report symptoms. This is obviously sensitive medical information that needs to be protected. At the same time, it could be useful to detect if, for example, suddenly many people report the same set of symptoms, to maybe detect possible emerging public health concerns and so on. So the components that we are going to use to solve this are the shuffled model of differential privacy, deep learning text embeddings models, and kernel densities in the Shuffled DP model. Let's start with Shuffled DP. It is a model for private distributed learning, which has been recently proposed as an intermediate model between the two classical models of differential privacy, the central one and the local one. The highlight is that it offers a strong notion of distributed privacy, also with good accuracy. That's all I have time to say in this video. For more information on this model, you can see our paper or those references that you see here. And a quick recap of what kernel density estimate is. It's a way to turn the dataset into a continuous density function that allows us to estimate the density of every point y in the space with respect to our dataset. In this case, it's the Gaussian density. KDE by itself does not preserve privacy, it leaks information about the dataset. A private KDE is a variant that approximately preserves the densities while also protecting the privacy of individual points in the dataset. The main theorem in this work is a KDE protocol in the Shuffled DP model. So if I have my privacy parameters epsilon and delta and my error parameter alpha, there is a protocol that computes an approximate density function k tilde, which is differentially private, and also its supremum root mean squared error in any point y in the space is at most alpha. And what you trade for this alpha is the computational efficiency, which is the running times of the user and the server, and the number of bits that they need to communicate. So let me make a point here about the distinction between central and shuffled DP in our case, and why it's meaningful here. In central DP, the users share their unprotected data with the server, and only then the server protects it to produce the approximate KDE function. This means that the server can compute the exact KDE, which in our case means it can learn what the texts are about by simply reading the text, which is not very interesting. In the Shuffled DP model, on the other hand, the data is already protected before it ever reaches the server. So the server cannot compute the exact KDE, and actually no party in this setup has the information needed to compute the exact KDE. Instead, this Shuffled DP protocol is going to compute an approximate KDE directly without going through the exact KDE, which means in our case that the server will be able to learn what the texts are about without actually reading any of the texts, which is what we want. So let's see how everything fits together. To solve private distributed topical decoding, first, every user will locally embed her text into R2D using some public text embedding model. Then they engage in this protocol, in the Shuffled DP protocol, to produce the approximate KDE function. Then the server can take a public vocabulary, embed every term in this vocabulary in R2D using the same public text embedding model, and measure the approximate density of every term in the vocabulary with respect to the dataset using this private KDE approximation, and output the terms that have the maximal density. Those terms are going to encompass or capture what the texts are about. Let's see some examples, experiments with typical setting of privacy parameters. In the first example, each user gets a text about an artist from Wikipedia. Some fraction of the users have off-topic text, just to have some outliers. And the top three terms that the KDE reports are artist, lyricist, and musician. So indeed, those terms encompass what the texts are about, even though the method cannot read any of the text. In the second example, each user gets a news article about sports. 20% of them get some news articles about some other topic. And the top three terms that the method reports are injury, semifinalists, and finalists. Again, terms that you expect to see in a corpus of news articles about sports. These are just examples. In the paper, you can see many other experiments. Also, there's other applications. I focus here on this topical decoding for concreteness. In the paper, we mostly focus on producing private KNN-like classifier from the distributed end-user data. So please see the paper for more, and thank you.